I'm going to be talking to Dr. Hydra Rodrigues, who is a technology analyst at IDTechEx, about a recent study she did on turning CO2 into plastics. So, welcome to the interview, Hydra.
Glad to be here. Thank you, Mark.
Now, this is a really interesting discussion to be having about North America in particular, because carbon capture, utilization, and storage is on the public agenda. The oil and gas industry, other industries want to use it to reduce their emissions. So the question becomes, what do you do with the CO2? And one option is to bury it underground in old oil and gas reservoirs. But there's also increasing attention being turned to turning CO2 into something else. So can you give us an overview of your study, please?
Absolutely. You're correct. The main question when capturing the CO2 is what to do with it. If you don't have an infrastructure, a pipeline running through your plant to capture that CO2 and put it on the ground, what can you do with it? So for decentralized emitters that are looking to capture their own emissions and then do something useful with it, carbon utilization has been put forward as being a solution. The way to do it, throughout our study, we understand that there are many ways of transforming CO2 into products. You can basically make anything that is fossil fuel based on using CO2 as a feedstock. If I were to summarize in 5 categories, the main ways of using CO2 is for enhanced oil recovery, when you inject CO2 on the ground to push more oil out and produce more oil. So that's CO2 used as a solvent. But the more emerging technologies that are coming for the CO2 utilization space is CO2 utilization in construction materials, where you mineralize that CO2 and put it into concrete or cement. There's also utilization of CO2 into the polymer manufacturing, where the molecule of CO2 is embedded within polymer chains. Or if you reduce that molecule of CO2, if you reduce it into its components, into carbon and oxygen, you can then utilize that carbon that is a bit more reactive and react it with other energy sources such as hydrogen and make hydrocarbons from it. And through that, you can make chemicals or fuels. And that has been explored on the especially in the aviation industry, to utilize fuels made out of CO2. The other pathways are a bit more established as well, apart from CO2 enhanced oil recovery, is to use the CO2 molecule as is. Don't need to break it into its components, because that's quite energy intensive. So looking at utilizing the CO2 in greenhouse crops to improve the yield of those crops within greenhouses, or in beverages, packaging, food conservation, and all of those applications.
Well, let's talk about using it in plastics. What are the three? I guess there are 3 major pathways to convert CO2 into polymers: electrochemistry, biological conversion, thermocatalysis. Could you explain those, please, just briefly, if you wouldn't mind?
Absolutely. The most mature way of transforming CO2 into polymers is the thermochemical pathway, where basically a novel catalyst allows the CO2 to be embedded within polymer structures. So that's a carboxylation reaction. The CO2 doesn't need to be broken down. Therefore, the energy requirement for that reaction it's lower than if you were to break the molecule. Up to 50% of those polymers, of those polyols, can be made from CO2, which will change the performance of that plastic. It's normally to make thermoplastics. The performance will be is slightly inferior to a fossil fuel based, a conventional fossil fuel based polymer in terms of mechanical characteristics. But that plastic will be biodegradable. That plastic will be malleable and can be used for many applications that are already used conventionally. This is the thermochemical pathway. The one that is more emerging now is the microbial pathway, which we call fermentation. Basically, engineered microbes can be feed off CO2 and an energy source, either hydrogen or methane. These molecules are a bit more expensive than CO2, but once the microbes feed up, they ferment the CO2 and this energy source, they can then create precursors make polymers. For example, ethanol or mag that can be then polymerized into polymers. And the interesting thing about this pathway is that the energy intensity is also lower. You don't need to put a lot of temperature and pressures because the microbe is doing all the work for you. And the last one is the electrochemical pathway, which is the least advanced. It's still in the lab and it's still in the demonstration projects, where an electrochemical cell, which is basically the opposite of a fuel cell, converts water into hydrogen and at the same time converts CO2 into CO, or carbon monoxide, that is more reactive than CO2. And then you can combine that hydrogen with the CO to make hydrocarbons.
Now, there's a lot of concern about plastic production these days. Recent OECD study found that in 2019, 460 million tons of plastic was produced in the world. And, it finds its way into the ocean and into ecosystems. And so there's a lot of concern about that. So I'm very interested in the idea of CO2-based polymers that are biodegradable. What can you tell us about that?
Yes, absolutely. There's one interesting pathway that has been proposed by one company in this space called New Light, where they use microbes to transform CO2 into a biodegradable polymer. And by biodegradable, it means it will be it's enzymatic biodegradable, so it will take a while to come back to the to Earth or to the atmosphere, but it will eventually go back. And that begs a question of, is this really reducing emissions? Because you basically delay the emission, right? You capture that emission from, let's say, a point source from a power plant, and then you transform it into a plastic. And at the end of the life of that plastic, it will biodegrade, the CO2 will be released in the atmosphere anyway. So you're just delaying the emission. But you need to think about the displacement of fossil fuel that created. Instead of using regular fossil fuels to make the polymers, you don't need to drill wells and extract more oil to make that those polymers. You can make it out of CO2 that is already going to the atmosphere anyway. And that idea of a cyclic, a carbon circular economy can be created. And the biodegradable part is also very important when you're looking at short-term plastic applications. A lot of the CO2 polymers are actually for long-term applications, for polyurethane that can be used to make mattresses, to make car parts, and these are more durable carbon sinks. If you have a mattress, you can have for decades, and that emission, instead of being contributed to climate change, contribute to global warming, is actually being stored in your house.
Are we getting to the point, Hydra, where we can make most of the things that we need in our modern life? And I'm thinking of clothes and furniture. You mentioned mattresses. Can we make them out of captured CO2?
That's an interesting utopia that might happen. We have the science. It is possible. The biggest bottlenecks to do it is the technical viability and the economic viability of it. So technical economic analysis is essential to understand that if that process will actually be profitable, but also would it be positive in terms of climate benefits? Because you need to think about not only the amount of CO2 that you are using from emissions, but also all the other emissions that will add to your supply chain if you were to transform your regular petrochemical process into a CO2-based process. So think of the retrofitting that you need to do, all the steel that you need to make those equipments for the capture of the CO2 and then the transformation of the CO2 into a product. Once you have that CO2 captured, how do you transport from point A to point B if you don't have co-location of the CO2 emission and the CO2 utilization? That CO2 needs to be transported somehow. And unfortunately, most of it, if you don't have high volumes like in the CO2 EOR industry, most of that CO2 is transported through trucks that might not be electrical. So all these emissions need to be taken into account. And then the overall life cycle needs to be a lower carbon footprint than if the conventional process were to be applied.
Is it fair to say that this industry is young and still in the formative stages? And if so, when might we see it become economic? And secondarily, for petrochemical clusters like we see in the U.S. Gulf Coast, or here in Canada we see in Alberta, are they capable then of adapting their existing plant to produce recyclable plastics?
Definitely, there is a potential there for this retrofitting, especially in the U.S. One of the biggest advantages is the independence of the feedstock. If you are able to capture the CO2 within your own plant or within your own cluster of petrochemical industry within that area in small scale, but just enough for your process, you don't need to be thinking about bigger supply chains. And depending on the source of the CO2, the costs might be even lower than sourcing regular fossil fuels. So one of the companies that we spoke to, they say that the ton of fossil fuel necessary to make polyurethane is around $1,000 per ton. And when you look at CO2, you can get a ton of CO2 depending on the source from $15 to max $150 if you're looking at point source CO2 captured. When you look at direct air captured CO2 from the air, then you're looking at $500 and etc. So it would be interesting to see from a decentralized point of view, all these plants, if they were able to source that CO2 and reduce the transportation costs, to start adopting the CO2 utilization. Now, how young is this industry? It's very young. It's a nascent industry. It's mostly, if you look at CO2 utilization space, is mostly dominated by CO2 enhanced oil recovery. We estimated that around 30.5 million tons of CO2 was used last year, and about 29 million tons of it was for CO2 UR. So very small amounts are used for all the other processes, for greenhouses, for mineralization, etc. Not accounting for ammonium and other utilization of CO2, but just anthropogenic CO2 that is captured from emissions. But we see an increasing a growth of this industry, and mostly it has happened in places that have policies that has incentives to create those to make it profitable. So CO2 UR is profitable. That's why it has happened. And the US is a good example with the 45Q tax credits that have incentivized the utilization of captured CO2.
Well, Hydra, thank you very much for your insights. Really appreciate this.
Thank you very much. Cheers.